This experiment is compression test on open coil spring, right? The objective of this experiment is again to find the modulus of rigidity, to find the modulus of rigidity and stiffness of the given open coil spring. This is a machine used for finding the modulus of rigidity of the machine. Here we have the dial. Here we can measure the load applied. Measure the load applied. Here we have the spring. Here one bottom plate is there and top plate is there. In between the two plates, the spring is fixed. Here we can apply the load. Here we can apply the load, and this is a experimental setup. The first step is the fixing the spring. Fixing the spring. Here you can see the spring. This is the way you have to fix it. Then you have to slowly move the top plate in touch with the spring. So that is the initial settings we have to do. So at that point, the top plate will be in light contact with the spring, top of the spring. So now you adjust the pointer to 0. Adjust the pointer to 0. Now you apply the load. Now you apply the load. So you can apply a 50 Newton load. 50 Newton load. Now you can see. So this is 100. This is starting point. From starting point to middle of this 100. So it is 50 Newton. 50 Newton load is applied. So corresponding deflection you can measure. Corresponding deflection you can measure from this scale. So initial reading must be noted. Before applying the load, the position of the pointer in the scale must be noted. So after applying the load, how much it is deflected, spring is deflected, that can be calculated from the initial reading and final reading. So that will give the deflection at the particular loading condition. So similarly, you have to apply 100 Newton, 150 up to 400 you can take reading. So it will get around 8 readings, 50, 100, 150, 200 up to 400. For 8 readings, the load as well as the deflection must be calculated, right? The initial reading, final reading you have to take. So that will give the deflection of the spring. The experiment can be repeated up to the 400 Newton. So every load you take the deflection of the spring. So after that you measure the outer diameter of the spring, then inner diameter of the spring, because in the calculation you will be using the mean diameter or radius you can use. So from that the mean diameter or radius can be calculated, and also you count the number of turns in the spring and the diameter of the wire. There are 2 diameters, one is wire diameter, another one is coil diameter. Both you measure, as well as number of turn also you measure. Then this is a tabulation. In the tabulation, while applying the load, you take the deflection of the spring. Similarly, while removing the load also, you have to take the deflection of the spring. You take the average of these two. Take the average of these two. Using these values, we have the value of load, we have the value of average value of spring deflection. Using this, you can find the modulus of rigidity, stiffness, shear stress, and strain energy stored. All these 4 values can be calculated. We have expression for this. This is a equation for modulus of rigidity. How this equation how the equation is derived? Already you have seen in the theory, right? Delta is equal to 64 W R cube N divided by G d power 4. That G is, if you take the G left side, you will get the equation like this. Similarly, stiffness of the spring, that is W by del, and shear stress. This equation also can be written in terms like, here it is in terms of radius. This also can be written in terms of diameter. If you write in terms of diameter, this will be 8 W d cube N divided by del d power 4. If you write this in terms of diameter, that will be 8 W d divided by pi d cube. Here it is written in terms of mean radius. Similarly, energy stored. You can use this equation, half into W into del. So here R value you have to calculate. Already we know the outer diameter and inner diameter. So R can be calculated by outer diameter plus inner diameter divided by 4. If you want diameter, you divide by 2. If you want radius, you divide by 4. So now we have all the details. For every reading, you calculate the modulus of rigidity, stiffness, shear stress, and strain energy stored. Strain energy stored. After that, the calculations. Then you draw the graph. In the graph, you have to draw between. You have to draw the graph between you have to draw the graph in between. Here you take the load. Here you take the load. Here you take the deflection. Deflection of the spring. This can be taken in mm. This can be taken in Newton. You will get a graph. You will get a graph like this. You will get a graph like this. So now you find the slope of this curve. Slope of this curve. That is dy by dx. What it will give? Load. Load is you take W. The deflection is theta. Deflection is theta. Deflection is x. Here we have taken deflection is del. So here load is W and deflection is del. We have taken. So now dy by dx, what is dy by dx? That is W by del. W by del. So this value you have to substitute in the modulus of rigidity equation. What is the equation for modulus of rigidity? This is 64 W R cube N by delta D power 4. This is the equation. Here W by del. W by del we have here. We have here. So if the W by del obtained from the graph must be substituted here. So now you will get C value. You will get C value. This is a value, C value, that is modulus of rigidity obtained from the graph, obtained by the graph. And you can also find the stiffness value. You can also, this is a stiffness. What is stiffness? W by del is the stiffness. Already this value itself stiffness. So you find this value also. So from the graph, you can find the value of modulus of rigidity as well as stiffness, This value must be compared with the value calculated from the equation. So here also we have calculated the value of G. We have calculated the value of G, modulus of rigidity. And here also we have calculated the value of stiffness. So you have to find the average of, you have calculated some 8 readings in G. So you find the average of G, similarly average of K. So that must be compared with the graphical value. But you don't find the average value for shear stress and strain energy. So this is value are and all not the property. It's not a property. So you need not calculate average for these values. Only for modulus of rigidity as well as stiffness. Right? So now come to the table. So in the table, you have to give the values. So in the graph, in the table, you must have calculated the modulus of rigidity, stiffness, shear stress, and strain energy. You don't take average of the shear stress and strain energy. Don't take this. This is not a property. So only modulus of rigidity and stiffness. You must have got 8 values. For 8, you take the average. You take the average. Similarly, for stiffness, you take the average. So this is value calculated from the formula expression. Similarly, you have the C value from the graph. So now you enter the values. Here you enter the values, right? Here modulus of rigidity from the formula from the graph. Here stiffness from the graph, from formula and from graph. Here shear stress value will vary from point to point. So you need not write these values. You need not write these values. You need not. It cannot be compared with the graph. You cannot calculate using graph. So you need not write these two. It cannot be compared. You need not write these two. Only you write these two, right? So then finally you got to write the results. That is average modulus of rigidity. Average modulus of rigidity. You got to write, right? Average modulus of rigidity. You write here. So this experiment is compression test on spring. So here a spring is compressed. A spring is compressed. So during compression, we have to take two readings. One is the load applied and displacement. Load applied and displacement. Two readings you got to take. From the two readings, you will be able to find the modulus of rigidity of this spring. Modulus of rigidity of the spring. That's what our objective. Our objective of this experiment is to find the modulus of rigidity of the spring material. Spring material. Here, the spring is here. We have the spring is here. Spring is here. It is fixed between two plates. Here there is a lower plate. Here there is upper plate. In between these two plates, a spring is fixed. Now you can apply the axial load. You can apply axial load using this handle. Here we have a handle. You can apply axial load using this handle or using motor. We have a motor also here. By pressing this, you can operate the motor. By using the motor also, you can apply the load. So for initial setting, we use the motor. After that, we use a handle for applying the load because we need to take reading at each and every point. So to stopping the motor at the exact point is difficult. So you use a handle, right? So here, how to find the modulus of rigidity? We have the relation between the load and deflection. There is an equation. The diameter of the coil in terms of radius, then the equation will be 64 W R cube N by G d power 4. G d power 4. Delta is equal to. So this is the equation. In the equation, we know the compression of the spring. Delta is known and load is known. And you can calculate the value of G. You can calculate the value of G, modulus of rigidity. This is experiments. So this dial is used for finding the load applied. Load applied. And you can get the value of deflection from this scale. Here there is a scale. In the scale, you can find the deflection. To apply the load, you use either handle or motor. So here spring is connected between the lower plate and upper plate. Lower plate and upper plate. This is the way you have to do the experiment. So now sir will demonstrate how to do the experiment. Sir. So now sir is operating the motor to initial setting. Initial setting. That means now see when just he operate the motor, this is rotating. The handle is rotating. So now the spring and the two plates are in compact. Now it is compact. Almost the top of the top plate is exactly touching the top surface of the spring. Now we are going to apply the load manually. Yes, here we have different scales. Here we are going to take in the outer reading. So now he is setting to 0. Now he is setting the reading to 0. And what my initial reading in the scale you have to note. Now it is, I think, say you can see in the needle, it is 50 Newton. Now you have to see the 40 point. Here the reading is given in centimeter. So the initial reading is 40.1. So the final reading is 40.4. So the difference is 0.3 centimeters. So it is 3 millimeters. It is 3 millimeters for the load of 50 Newton. For the load of 50 Newton, the deflection is 3 millimeter. Right? So now I apply the load again. Now he is applying the load by rotating the handle. So it is 100. So now he is applying 100 newtons.
Now the load is 100 Newton. Now the load in the needle is 100 Newton. Now deflection, he is seeing the deflection 40.6. So initial reading is 40.1. 40.1. Now it is 40.6. So the initial reading is 40.1. The final reading is 40.6. That is 0.5 centimeters. That is equal to 5 millimeters. Now again you apply the load. The load is 150 Newton. Load is 150 Newton. Deflection is 40.8. 40.8. What is the initial reading? 40.1. Then the deflection is 0.7 centimeter. That is 7 millimeter. For 150 Newton load, the deflection is 7 millimeters. Again, you apply the load. Now he is applying. So now he applied 200 Newton load and seeing the corresponding displacement. It is 40.9. So what is the net deflection? 40.9 minus 40.1. It is 0.8 centimeter. That is 8 millimeter. 8 millimeter corresponding to 200 Newton force. 200 Newton force. Again, you apply the load. So now the load is 250 Newton. And the corresponding deflection is, it is 41. It is 41. So 41 minus 40.1. It is 0.9 centimeter. That is 9 millimeter. This is corresponding to 250 Newton. Now he is applying 300 Newtons. 41.1 minus 40.1. It is 1 centimeter. That is 10 millimeters. 10 millimeters corresponding to the 300 Newton force. Now again he is applying a load of 350 Newton. 41.2. 41.2 minus 40.1. 1.1 centimeter. That is 11 millimeter for 350 Newton load. Again, the final load he is applying 400 Newton. 41.4. 41.4 minus 40.1. So it is 1.3 centimeters, 13 millimeters for 400 Newton force. Now during applying the load, while removing the load also you have to take the reading. So the readings are, when 350 Newton is applied, the reading is 41.3. Already we know the initial reading is 40.1. The difference is 1.2 centimeters. That is equal to 12 millimeters. Now again apply the load. Again remove the load. Now the load is 300 Newtons. The corresponding deflection is 41. The initial reading is 40.1. The difference is 0.9 centimeters. Now the in millimeter it is 9 millimeter. Again you reduce the load. For 250 Newton, the deflection is 40.9. You minus initial reading, that gives you the 0.8 centimeter. That is equal to 8 millimeters. Again you reduce the load. For 200 Newtons, the reading is 40.8 minus initial reading, that gives you 0.7 centimeter. That is 7 millimeters. Again reduce the load, that is 150 millimeter. The reading is 40.6 and the deflection is, the difference in from the initial is, it is 0.5 centimeter. That is 5 millimeters. Again reduce the load, it is 100 Newton load. The deflection is 40.5 minus 40.1. That gives you 0.4 centimeter. That is 4 millimeter. So finally for 50 Newton load, the displacement reading is 40.4 minus initial reading, that is 40.1. That is equal to 0.3 centimeter. That is 3 millimeter. So now we have the load, and while increasing the load we have deflection. While decreasing the load you have the deflection. So you find the average. You find the average, and you do the calculation for the average value. The parameters of the spring also for calculation of modulus of rigidity. So this is wire diameter. So the coil is made up of wire. The wire has a diameter. So diameter of the wire, that is 7 millimeters. And the spring is made into coils. So the coil have a diameter. The coil have a diameter. the diameter of the coil is, it has inner diameter and outer diameter. Outer diameter is 60, inner diameter is 46 millimeters. You have to find the mean diameter. You have to find the mean diameter. So 60 plus 46 divided by 2. That will be the mean coil diameter. And the wire diameter is 7 millimeter. It has 5 springs. It has 1, 2, 3, 4, 5. There are 5 springs. There are 5 springs. 1, 2, 3, 4, and 5. You can see 1, 2, 3, 4, and 5. There are 5 springs. So number of coil in the spring is 5. N is equal to 5. And the wire diameter, small d, is equal to 7 millimeters. And the coil diameter is 60 plus 46 by 2. So this dimension also you have to use in the calculation of modulus of rigidity.